Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
A peculiar and profound crisis haunted theoretical physics in the years following the Second World War. It was a crisis born of spectacular success. The theory of quantum electrodynamics, or QID, the quantum theory of light and matter, had emerged from the minds of Richard Feynman, Julian Schwinger, and Sinnatiro Tominaga as a calculational tool of almost supernatural precision. Its predictions for the interactions between electrons and photons were confirmed by experiment to an astonishing degree of accuracy. The archetypal example, a result that would echo through the coming decades, was Lamb shift. In 1947, Willis Lamb and Robert Rutherford measured a tiny, unexpected difference in the energy levels of the hydrogen atom. The existing Dirac theory of the electron predicted these levels should be identical. Yet, the experiment revealed a separation, a subtle whisper from the quantum vacuum. Within months, Hans Bethe produced a quick, non-relativistic calculation that explained the effect as a consequence of the electron's interaction with the seething fluctuations of the electromagnetic field. Soon after, the full relativistic machinery of QED was brought to bear, yielding a theoretical value for the Lamb shift that matched the experimental one to an unprecedented number of decimal places. This was a triumph of the highest order, a moment that should have cemented the foundations of physics for a generation. Instead, it exposed a deep, unsettling fracture. The calculations that produced the beautiful, correct numbers were, from a mathematical perspective, complete nonsense. The process, known as renormalization, involved manipulating expressions that were formally infinite. Physicists learned to start with divergent integrals representing quantities like the bare mass and charge of an electron, and then systematically subtract other, equally infinite quantities in a carefully prescribed way. The procedure worked. It yielded finite, verifiable answers. For many physicists, particularly Feynman, this was sufficient. He famously developed a pragmatic, instrumentalist view. The theory was a set of rules, and as long as the rules gave the right answer, their logical coherence was a secondary concern. His attitude, often summarized as a directive to shut up and calculate, captured the spirit of a generation eager to push the frontiers of prediction. This approach, however, caused profound intellectual discomfort for another community. Mathematicians and physicists with a mathematical conscience looked upon these procedures with something approaching horror. The entire edifice of QED appeared to be built on a foundation of sand, a collection of ad hoc prescriptions and clever tricks for sweeping infinities under the rug. The great John von Neumann, who had single-handedly placed the earlier theory of non-relativistic quantum mechanics on the unshakable bedrock of Hilbert spaces and operator algebras, was famously dismissive. To him, the renormalization program was a shell game, a mathematically unprincipled maneuver. He saw a theory whose phenomenal predictive power was completely divorced from any form of mathematical rigor. The central problem was clear: physics had produced its most successful theory, and it had absolutely no idea what it was, mathematically speaking. The equations seemed to describe a world of infinite energies, infinite probabilities, and ill-defined objects, which were then tamed by a set of recipes that lacked any logical justification. The crisis was one of meaning. What asterisk is asterisk a quantum field? What is the mathematical space in which it lives? How can a theory be built from the ground up to respect both the principles of relativity and quantum mechanics without collapsing into a cascade of infinities? Into this intellectual breach stepped Arthur Wightman, a physicist from Yale and later Princeton. Wightman possessed a unique temperament. He combined the physical intuition of a theorist with the exacting standards of a pure mathematician. He took the mathematical incoherence of quantum field theory as his life's primary intellectual challenge. His ambition was monumental in its scope to do for relativistic quantum field theory what von Neumann had done for quantum mechanics. He sought to construct a complete, rigorous, and logically sound framework for the entire subject. This meant turning away from the immediate, pragmatic goal of calculating scattering amplitudes. The objective became something far more fundamental. He wanted to define, with axiomatic precision, what a quantum field theory could be. The purpose was to build a solid foundation upon which theories could be constructed and analyzed, to create a language in which one could ask, and perhaps answer, whether a theory like QED could exist as a consistent mathematical structure. Wightman's program was an exercise in deep synthesis, drawing upon the most powerful mathematical ideas of his time to give form to physical principles. His approach was directly shaped by the towering achievements of his predecessors. From John von Neumann, he inherited the entire conceptual paradigm of using abstract functional analysis as the natural language of quantum theory. Von Neumann's 1932 book, Mathematical Foundations of Quantum Mechanics, demonstrated that the strange postulates of the quantum world, states as vectors, observables as operators, probabilities as inner products, found their perfect home in the theory of Hilbert spaces. Wightman saw this as the essential template. A proper quantum field theory would likewise have to be defined in terms of operators acting on a Hilbert space of states. The challenge was to adapt this framework to accommodate the additional, stringent demands of Einstein's special relativity. For this, he turned to the seminal work of another Princeton luminary, Eugene Wigner. In a landmark 1939 paper, Wigner had used the mathematical theory of group representations to analyze the symmetries of spacetime. He showed that the fundamental properties of an elementary particle, its mass, and its spin, are labels that characterize how the quantum state of that particle transforms under the symmetries of the Poincare group, the group of all rotations, boosts, and spacetime translations. Wigner's analysis provided a profoundly deep connection between symmetry and the very definition of a particle. It was a piece of mathematics so fundamental that any attempt to build a relativistic quantum theory had to incorporate it from the outset. Wightman understood that a rigorous theory of quantum fields must begin with a Hilbert space of states that carries a unitary representation of this Poincare group, thereby encoding the principles of special relativity into the very fabric of the theory. With the tools of operator algebras from von Neumann and the group theoretic language of relativity from Wigner, Wightman began to formulate his grand project. He proposed to distill the core physical requirements of any sensible relativistic quantum theory into a small, powerful set of axioms. These axioms would serve as the constitution for the universe of possible quantum field theories. They would be statements about the nature of states, the properties of fields, the structure of spacetime, and the principle of causality, all expressed in a language of uncompromising mathematical precision. His work would shift the very nature of the questions being asked. The focus would move from the pragmatic art of calculation to the foundational science of definition. This axiomatic approach promised a path out of the wilderness of infinities, a way to construct a solid ground from which one could survey the landscape of physical reality. The first step on this path involved a radical reconceptualization of the quantum field itself, a step that would require one of the most powerful new ideas in 20th century mathematics. The intellectual apparatus required for this reconstruction began to assemble in collaboration between Wightman and the Swedish mathematician Lars Gårding. Their shared ambition was to erect a framework for quantum field theory with the same logical solidity that David Hilbert and John von Neumann had given to elementary quantum mechanics. The result of their efforts, the Gårding-Wightman axioms, represents one of the great intellectual achievements of 20th century physics. Each axiom is a response to a deep physical question, a piece of mathematical machinery precision engineered to enforce a fundamental principle of reality. The first challenge was to define the very arena in which physical phenomena unfold. What is the mathematical space that holds all possible states of a relativistic quantum system? The answer began with the familiar concept of a Hilbert space, the abstract vector space that serves as the bedrock of quantum theory, where states are represented by vectors and physical observables by operators. This provided the quantum mechanical aspect. The relativistic component demanded something more. Any viable theory must look the same to all inertial observers, whether they're stationary or moving at a constant velocity. This principle of relativistic covariance, the heart of Einstein's special relativity, needed to be woven into the fabric of the state space itself. Wightman's solution was to demand that this Hilbert space carry a specific kind of mathematical structure, a continuous unitary representation of the Poincare group. The Poincare group is a full symmetry group of special relativity, encompassing translations in space and time, rotations in space, and the more subtle Lorentz boosts that connect observers in relative motion. By requiring a unitary representation, the axiom ensures that for every transformation in spacetime, a shift, a turn, a boost, there is a corresponding transformation on the quantum states that preserves all physical probabilities. A physicist performing an experiment in a laboratory flying past Earth at near light speed would describe states with different coordinates, yet the underlying physical laws and predictions encoded in the inner products of the Hilbert space would remain absolutely invariant. This axiom establishes a profound dictionary, translating the geometry of spacetime into the operator algebra of quantum mechanics. With the stage set, the next imperative was to ensure the drummer enacted upon it was physically sensible. A universe with an unstable vacuum, a system that could shed infinite amounts of energy, is a physical absurdity. The second axiom, the spectrum condition, provides the bulwark against this catastrophe. It addresses the properties of the energy and momentum of physical states. In quantum mechanics, energy and momentum are the eigenvalues of the operators that generate translations in time and space. The spectrum condition is a powerful geometric constraint on these eigenvalues. It postulates that the form momentum vector, the vector whose time component is energy and whose spatial components form the momentum vector for any physical state, must lie within the forward light cone in momentum space. This geometric statement has immediate, profound physical consequences. It means that for any state, the energy is always positive or zero, and that the energy squared is always greater than or equal to the square of the momentum times c squared. This condition automatically guarantees the existence of a state with the lowest possible energy, a state with zero energy and zero momentum. This unique state is the vacuum, the stable, invariant ground state of the universe. The spectrum condition thus elegantly enforces the stability of all matter, preventing the spontaneous decay of everything into an abyss of negative energy. It is the mathematical guarantee that the vacuum is truly empty and that physical reality has a solid floor. The most revolutionary step in the axiomatic program concerned the nature of the quantum field itself. The calculations of quantum electrodynamics were plagued by infinities that arose whenever physicists tried to treat quantum fields as classical fields, assigning a definite operator value to each point in space-time. These fields fluctuated with such violence that their value at a point was a meaningless, infinite quantity. Wightman, possessing a deep appreciation for the latest developments in pure mathematics, saw the solution in the work of the French mathematician Laurent Schwartz. Schwartz had recently formalized the theory of distributions, or generalized functions, a framework for dealing with objects too singular to be conventional functions. Wightman's third axiom makes the audacious claim that a quantum field is an operator-valued, tempered distribution. The field is a machine that only produces a well-defined, bounded operator when it is fed a smooth, well-behaved test function. This process is often called smearing. One can visualize this by imagining the field as a map of temperature. Asking for the temperature at a single mathematical point is physically meaningless and could yield a wild, infinite answer due to quantum fluctuations. A real thermometer, however, has a finite size. It measures the average temperature over a small volume. The smearing of the quantum field with a test function is the mathematical analog of this physical reality. By averaging or smearing the field over a small region of spacetime, its violent short-distance fluctuations are tamed, yielding a finite, physically meaningful operator. This conceptual masterstroke, directly inspired by Schwartz's work, sidestepped the problem of infinities by redefining the fundamental object of the theory. The quantum field became a smeared object, aligning mathematical formalism with the reality of any possible physical measurement. Finally, the framework needed to incorporate the most sacred principle of relativity, causality. An effect cannot precede its cause, and no influence can travel faster than the speed of light. To encode this, Wightman introduced the axiom of microcausality, or local commutativity. This axiom connects the algebraic properties of the field operators to the causal structure of spacetime. It states that if you take two field operators, each smeared over a distinct region of spacetime, these two operators must commute whenever the regions are space-like separated. Two regions are space-like separated if the light signal cannot travel from one to the other. They are causally disconnected. The physical meaning of commutation is that the order of measurement is relevant. Measuring the field in region A and then in region B yields the identical outcome as measuring the field in region B and then in region A. This algebraic condition is the precise mathematical expression of Einstein's principle of locality. It guarantees that that a measurement performed on the moon can have absolutely no instantaneous influence on the outcome of an experiment in a laboratory on Earth. For fields describing fermions, like electrons, the condition is slightly modified to anti-commutation, a subtlety that would prove to have immense consequences. This axiom forges the final, crucial link, ensuring that the quantum theory respects the fundamental causal ordering of the universe. Together, these axioms formed a complete and self-consistent logical structure that provided a clear, unambiguous definition of what constitutes a relativistic quantum field theory. The architecture of this new edifice was complete. Its structural integrity would now be tested by its ability to support the foundational pillars of physical law, transforming long-held empirical rules and heuristic arguments into inescapable, logical certainties with the axiomatic framework established. The question became one of consequence. A beautiful logical structure is one thing, a powerful engine of discovery is another. The value of Wightman's edifice would be measured by its ability to derive from its abstract principles the concrete and unyielding laws of the physical world. This was a moment of payoff, where the immense intellectual investment in rigor was to yield its dividends in the currency of physical insight. The axioms were about to be put to work, transforming empirical observations and heuristic arguments into the crystalline certainty of mathematical theorems. The first great pillar to be secured by this new foundation was the statistics theorem. For decades, physicists operated with a profound and empirically infallible rule, first given a deep quantum mechanical basis by Wolfgang Pauli. Particles with integer spin photons, gluons, the Higgs boson, behave as bosons. They obey Bose-Einstein statistics, a form of quantum gregariousness that allows identical particles to occupy the same quantum state, leading to phenomena like laser light and superconductivity. Conversely, particles with half-integer spin electrons, protons, quarks, or fermions, they obey Fermi direct statistics and are governed by the Pauli exclusion principle, a quantum standoffishness that forbids them from sharing a state. This principle is responsible for the structure of the periodic table and the stability of matter itself. The connection was known to be true. The reason for its absolute necessity remained a puzzle awaiting a complete explanation. The Wightman axioms provided the machinery for a definitive proof. The argument weaves together the axiom of relativistic invariance with the axiom of microcausality in a display of deductive force. Relativistic invariance dictates how quantum fields must transform under the operations of the Poincare group, which includes rotations. The mathematical theory of this group's representations shows that fields come in two fundamental types: those that return to their original state after a 360-degree rotation, corresponding to integer spin, and those that acquire a minus sign, returning to their original state only after a 730-degree rotation, corresponding to half-integer spin. Microcausality, meanwhile, imposes its own stern demand. Measurements at 2 points separated by a space-like interval must be compatible. This compatibility takes the form of either commutation or anti-commutation of the corresponding field operators. The proof demonstrates that these two principles, when combined, leave zero room for negotiation. If one attempts to construct a theory of a half-integer spin field, like an electron, using commutation relations, treating it like a boson, a catastrophic inconsistency emerges. The analytic properties of the Wightman functions, which are correlation functions between fields at different spacetime points, become pathological. Specifically, the requirement that these functions be consistent with both Lorentz symmetry and the spectrum condition positive energy forces, a violation of microcausality for any space-like separation. An experiment in one location could instantaneously affect another, tearing apart the causal fabric of spacetime. The only way to restore locality for a spin one-half field is to impose anti-commutation relations. The axioms compel the Pauli exclusion principle. The same logic applies in reverse for integer spin fields, forcing them into the mold of bosons. The spin statistics connection was thus elevated from a deep physical rule to an inescapable consequence of the very first principles of relativistic quantum theory. A second, perhaps even more profound, triumph for the axiomatic program came with the CPT theorem. Physics in the mid-20th century was grappling with the discovery that certain discrete symmetries of nature were imperfect. Parity, or P, the symmetry of mirror reflection, was found to be violated in the weak nuclear force, a discovery that stunned the physics community. Charge conjugation, or C, the symmetry of swapping particles for their antiparticles, was likewise found to be broken. With these cherished symmetries falling, a critical question emerged: does any fundamental discrete symmetry remain inviolate? The answer came from Jost, a brilliant Swiss mathematical physicist whose work was deeply interwoven with the axiomatic school flourishing around Princeton. In 1957, Jost produced a proof of breathtaking elegance, demonstrating that any theory satisfying the Wightman axioms must be invariant under the combined operation of C, P, and T, time reversal. The CPT theorem asserts that the laws of physics are unchanged if one simultaneously swaps all particles with their antiparticles, reflects all spatial coordinates in a mirror, and runs the arrow of time backwards. Jost's proof was a tour de force of complex analysis applied to the Wightman functions. He showed that the axioms of Lorentz invariance, locality, and the spectrum condition endow the Wightman functions with powerful analytic properties. They can be analytically continued from real spacetime coordinates into a specific domain of complex spacetime coordinates. Within this complex landscape, the CPT transformation corresponds to a simple geometric operation, a rotation, by an angle of pi. The constraints imposed by the axioms guarantee that this rotation leaves the functions entirely unchanged. A symmetry is automatic, is a built-in structural feature of any theory that marries quantum mechanics with special relativity in a locally causal way. The existence of this deep symmetry was revealed through the mathematical lens of the axiomatic framework. It implies, for instance, that every particle must have an antiparticle with an identical mass and lifetime. The CPT theorem stands as one of the most robust and fundamental principles of modern physics, and its rigorous derivation was a crowning achievement for Wightman's approach. These successes demonstrated the deductive power of the axioms. A third key result revealed their constructive and conceptual power, the Wightman reconstruction theorem. This theorem addresses a foundational question: what is the minimal set of data required to define a quantum field theory? A physicist might begin with the Lagrangian, a Hilbert space, and a set of field operators. The reconstruction theorem shows that this is far more information than necessary. The entire theoretical apparatus, the Hilbert space of quantum states, the field operators that create and destroy particles, and the action of the Poincare group that governs spacetime transformations can be reconstructed from a single, specific set of inputs. These inputs are the Wightman functions themselves, the complete collection of vacuum expectation values for all products of field operators. Think of them as the theory's genetic code. If one is given a list of these functions, say w sub n of x1, x2, up to xn for all n, and this list satisfies the properties dictated by the axioms, covariance, locality, positivity, and the spectrum condition, then a unique quantum field theory corresponds to it. The theorem provides the recipe for this reconstruction. The crucial ingredient is the positivity condition, which is a mathematical statement ensuring that probabilities are always positive. This condition allows for the use of a powerful mathematical tool called the Gelfand-Marseille construction to build the theory's Hilbert space from the algebra of the fields. From there, the field operators and the vacuum state find their natural home. The implications of the reconstruction theorem are immense. It provides a complete conceptual clarification of what quantum field theory asterisk is asterisk. The theory asterisk is asterisk its set of correlation functions. This perspective deeply influenced parallel developments in theoretical physics, particularly the algebraic approach to quantum field theory pioneered by Rudolf Karg and Daniel Kazar. Their work, which formulates QFT in terms of local algebras of observables, shares the same spirit of identifying the essential mathematical soul of the theory, moving away from the redundant scaffolding of traditional formulations. Through these three monumental results, the axiomatic program demonstrated its profound worth. It forged a logical chain from the abstract principles of relativity and quantum causality to the concrete, observable facts of the universe, like the behavior of electrons and photons. The framework had proven its structural integrity and its deductive might. It had answered the question of what any reasonable theory must look like. A far more difficult question, however, loomed on the horizons. Could one use this pristine blueprint to actually construct a theory describing the rich, interacting world of particles we observe it through these three monumental results? The axiomatic program demonstrated its profound worth. It forged a logical chain from the abstract principles of relativity and quantum causality to the concrete, observable facts of the universe, like the behavior of electrons and photons. The framework had proven its structural integrity and its deductive might. It had answered the question of what any reasonable theory must look like. A far more difficult question, however, loomed on the horizons. Could one use this pristine blueprint to actually construct a theory describing the rich, interacting world of particles we observe? The chasm between defining a structure and inhabiting it proved to be terrifyingly vast. For decades, theoretical physicists had relied on a powerful computational scheme known as perturbation theory. This approach began with a simple, soluble theory of non-interacting, or free, particles, and then introduced interactions as small, successive corrections. The mathematical machinery for this, the interaction picture, was the engine of quantum electrodynamics, producing predictions of astonishing accuracy. It was a bedrock of calculation, yet a devastating result from the German mathematical physicist Rudolf Karg, a close contemporary and intellectual cousin of Wightman, revealed this bedrock to be built on a logical paradox. Karg's theorem, in its various formulations throughout the 1950s, delivered a stark and unsettling conclusion. It demonstrated that the foundational assumption of the interaction picture was mathematically inconsistent with the core axioms of relativistic quantum field theory. The theorem's technical core is subtle, but its implication is breathtakingly direct. The Hilbert space of states for an interacting theory, and the Hilbert space for its corresponding free theory, are unitarily inequivalent. There is no well-behaved mathematical transformation, no simple change of basis, that can connect the world of interacting particles to the idealized world of free ones. They are, from a rigorous standpoint, entirely separate universes. The physicist's trick of turning on an interaction was, axiomatically speaking, an illicit leap across an unbridgeable void. This created a profound schism in the heart of theoretical physics. On one side were the practitioners, using perturbative methods to calculate quantities like the anomalous magnetic moment of the electron to stunning precision. On the other were the purists like Wightman, whose own framework showed that these very methods were, in a deep sense, ill-defined. The success of the calculations was undeniable. Their mathematical foundation, however, appeared to be absent. The Wightman axioms, which had so beautifully captured the essence of what a theory ought to be, seemed to forbid the existence of the very tools used to connect theory with experiment. The elegant axiomatic cathedral stood magnificent and proud, yet it appeared to be entirely empty. The pressing intellectual task became one of proving that at least one non-trivial, interacting theory could actually lie inside it. Wightman's response to this crisis was characteristic of his entire intellectual temperament. He viewed Karg's theorem as a profound insight, a signpost pointing toward a deeper truth. It revealed that interactions in quantum field theory were an intrinsically non-perturbative phenomenon. They altered the very vacuum state and the nature of particles so fundamentally that they could never be treated as a mere add-on. This realization spurred him to champion a new, audacious research program that would become known as constructive quantum field theory. The goal was immense: to construct explicit, mathematically rigorous examples of interacting quantum field theories that satisfy the full set of Wightman axioms from the ground up, without any reliance on perturbative expansions. It was a shift from defining the rules of the game to proving that the game could actually be played. This endeavor required a strategic retreat to a more manageable battlefield. The full complexity of four-dimensional spacetime, with its intricate ultraviolet and infrared divergences, presented a fortress of analytic difficulties. The constructive program therefore began in low-dimensional worlds, quantum mechanics in one-dimension time alone, and then, crucially, field theory in two-dimensional spacetime, one space in one time dimension. Within this simplified setting, the hope was to develop the powerful mathematical technology needed for an eventual assault on the four-dimensional reality. The heroic figures of this new program were two of Wightman's brilliant younger colleagues at Harvard and later Princeton, James Glim and Arthur Jeff. Directly inspired and championed by Wightman, they embarked on a multi-year quest to solve what was perhaps the simplest non-trivial model imaginable: a scalar field in two dimensions interacting with itself through a polynomial potential, a theory known as P phi sub 2. The challenge was immense. requiring the importation and invention of sophisticated tools from functional analysis. A key technique was the cluster expansion, a method borrowed from statistical mechanics for analyzing systems of interacting particles at high temperatures. Glim and Jeff adapted this tool to the quantum field theory context, using it to control the behavior of the theory as the volume of space was taken to infinity. Their eventual success, published in a series of landmark papers in the late 1960s and early 1970s, constituted one of the great achievements of the 20th century mathematical physics. They proved, with complete mathematical rigor, that the P-phi sub 2 theory exists and satisfies all of the Wightman axioms. For the first time, there was an explicit, undeniable example of an interacting relativistic quantum field theory. The axiomatic program was vindicated. The cathedral was inhabited. This triumph, while confined to 2 dimensions, was a monumental proof of principle. It demonstrated that the demand for mathematical rigor was a fruitful enterprise capable of producing concrete existence theorems for theories of genuine physical interest. The work of Glim, J.F., and other pioneers of the constructive school had consequences reaching far beyond the validation of Wightman's axioms. The methods they developed forged a deep and powerful connection between quantum field theory and classical statistical mechanics. This bridge was built upon the concept of Wick rotation, a formal trick where calculations in relativistic spacetime with its Minkowski metric are transformed into problems in Euclidean space. In this Euclidean formulation, the quantum field theory path integral becomes mathematically analogous to the partition function of a statistical mechanics system. A quantum field theory in D dimensions looks like a statistical system in D dimensions. This correspondence became a two-way superhighway for ideas. Concepts from statistical physics, light-phase transitions, and critical phenomena found natural expression in the language of quantum field theory. Conversely, the powerful machinery of quantum field theory, particularly the renormalization group, provided a profound new framework for understanding the universal behavior of matter near a critical point. The rigorous, non-perturbative methods developed by the constructive school to tame the infinities of quantum field theory provided the solid, mathematical foundation that the physicist Kenneth Wilson's more intuitive formulation of the renormalization group had previously lacked. The effort to construct quantum fields had led directly to a deeper understanding of the collective behavior of matter, one of the central problems in condensed matter physics. Wightman's quest for logical coherence within the quantum world had unexpectedly illuminated the mathematical structure governing everything from boiling water to magnetized iron. The wall presented by Hart's theorem had been surmounted, and on the other side lay a rich and fertile landscape of interconnected ideas, demonstrating that the pursuit of absolute rigor could yield rewards of astonishing breadth and power. The intellectual triumph of connecting constructive field theory to the renormalization group underscored a deeper imperative: the need to cultivate a new generation of physicists fluent in this demanding language of mathematical truth. The construction of quantum fields in lower dimensions was a monumental proof of principle. Ensuring its philosophy would permeate the culture of theoretical physics required a different kind of construction, the building of a school of thought. Arthur Wightman's influence, therefore, extended far beyond his own research papers and axiomatic frameworks. It found its most lasting expression in the minds he shaped and the intellectual standards he propagated, creating a living tradition of mathematical physics centered at Princeton University. This pedagogical mission was powerfully crystallized in a single, legendary volume. In 1964, collaborating with his former student Ray Streeter, Wightman published PCT, Spin and Statistics, and All That. The book's title, with its slightly whimsical final clause, belies the absolute seriousness of its contents. This was a textbook, a research monograph, and a manifesto rolled into one. It presented the foundational results of axiomatic quantum field theory with uncompromising clarity and rigor. For students accustomed to the brilliant, intuitive, and often hand-waving arguments of mainstream physics texts, reading Streeter and Wightman was a bracing, almost shocking experience. Every concept, from the definition of a relativistic quantum field to the derivation of the connection between spin and statistics, was built upon a solid foundation of functional analysis and distribution theory. The book taught a generation of aspiring theorists that concepts like the Poincare group, tempered distributions, and the spectral condition were the authentic language for discussing fundamental physics. The work's purpose was to demonstrate that deep physical principles like the CPT theorem, which asserts the combined symmetry, the charge conjugation, parity inversion, and time reversal, could be derived as inescapable mathematical consequences of a few fundamental assumptions. The book took readers on a direct, logical path from the axioms to these profound results, showing that they were embedded in the very structure of a relativistic quantum theory. It was a pedagogical tour de force that armed its readers with the tools to think about quantum field theory with a level of precision previously reserved for pure mathematics. Its influence was immense. It became the foundational text for anyone wishing to enter the field of mathematical physics, setting a standard of argumentation that continues to shape the discipline. Through this book, the Wightman program became a reproducible intellectual technology capable of being learned, applied, and extended by others. This textual legacy was magnified by Wightman's personal presence at Princeton. In the corridors of Jadwin Hall, he cultivated an intellectual environment of legendary intensity. His group of graduate students and postdoctoral fellows became the nucleus of what some affectionately, and perhaps with a touch of awe, referred to as the Jadwin cult. This was a group bound by a shared commitment to solving the foundational problems of quantum field theory with complete mathematical honesty. Wightman's mentorship style was Socratic and famously demanding. He would guide his students toward a problem, provide the essential conceptual tools, and then leave them to grapple with the immense technical challenges, always available for consultation, but insistent that they forge their own path to a solution. From this crucible emerged a remarkable lineage of mathematical physicists who would go on to define the field for the subsequent 50 years. His students included figures like Arthur J.F., who would become a central leader in the constructive field theory program, Oscar Langford III, whose work on statistical mechanics and dynamical systems brought a new level of rigor to those fields. Barry Simon, one of the most prolific and influential mathematical physicists of all time, whose work spans the entire spectrum of the discipline, and Edward Nelson, whose own unique approach to constructive theory using stochastic mechanics provided a fascinating alternative perspective. Each of these figures, and many others, carried Wightman's intellectual DNA forward. They inherited his deep respect for physical intuition, combined with an unwavering insistence that this intuition be translated into precise, provable mathematical statements. He taught them that the highest form of understanding in theoretical physics was a beautiful proof. Ultimately, the measure of Arthur Wightman's career resides in the enduring intellectual quest he championed. The specific axiomatic system he formulated, while a landmark of conceptual clarity, has faced profound challenges in accommodating the non-ably engaged theories that form the heart of the standard model of particle physics. The framework, in its original form, struggles to describe the dynamics of quarks and gluons. Yet, to focus on this limitation is to miss the deeper significance of his life's work. His most powerful contribution was the permanent establishment of mathematical physics as a kind of loyal opposition within the theoretical physics community, a critical, internal voice demanding coherence and logical consistency. He demonstrated, with incontrovertible force, that the demand for rigor is a powerful engine of discovery. It was this very insistence on a well-defined mathematical structure that led to the formulation of Hard's theorem, a result that appeared to be a roadblock but was in fact a crucial signpost revealing a deep and counterintuitive truth about the nature of interacting quantum fields. The entire program of constructive field theory, with its eventual connections to the renormalization group in statistical mechanics, was born from the conviction that the problems of quantum field theory were mathematical problems requiring mathematical solutions. Wightman's work transformed the perception of mathematical rigor from a sterile exercise in dotting I's and crossing T's into a creative and indispensable tool for probing the fundamental structure of reality. This tradition is his true legacy. It lives on today in the most advanced frontiers of theoretical physics, in the ongoing search for a theory of quantum gravity, in the labyrinthine world of string theory and M-theory. The dialogue between bold physical speculation and the constraints of mathematical consistency is more vital than ever. The central challenge remains the same as the one Wightman identified decades ago: how to build a theoretical structure that is both physically predictive and mathematically sound. The intellectual heirs of Wightman continue this quest, armed with the understanding that the laws of nature, whatever their ultimate form, must be expressible in a language that is free of contradiction and ambiguity. Arthur Wightman's great contribution was to spend a lifetime refining that language, teaching it to others, and demonstrating that the search for mathematical truth and the search for physical reality are, at their deepest level, one and the same.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.